Section 8.4, vectors. Alright, we have some stuff written down here. Scalars are quantities that are described by a single value called a magnitude. And magnitude is the size or measurement of the quantity. And vectors are quantities that are described by both magnitude and direction. Alright, so a scalar would be something like this ship's traveling at 20 miles per hour. Okay, 20 miles per hour would be like a scalar quantity, okay? It just describes a single value. Alright, vectors are quantities described by both magnitude and direction. So if I would say the ship was traveling 20 miles per hour north, 30 degrees west, then that would give me both a speed and a direction. So that would be a vector. Alright, what we do, we draw visual representations of vectors. We usually have a point here, a point there, and an arrow going in the direction of something like a ship or an airplane or whatever, okay? And we have a few things we need to talk about here. This point right here is called my initial point. Initial point of my vector. And over here, this point that's by my arrow is called my terminal point. Terminal point in my vector. Now, we could call this vector, vector AB like this. AB with an arrow above it, or I could call this vector U with an arrow above it. Okay, either one of those are fine. Now, whenever you read a textbook or Alex or whatever, they're probably going to have AB in bold-faced or U in boldface, okay? It's just, that means the same thing as this, and AB in boldface means the same thing as that. It's just it's hard for us to draw boldface when we're handwriting. So that's why we end up putting AB with just an arrow over instead. Alright, so we have initial point, terminal point, and we can call that vector either vector AB, vector U, okay? Now, your book goes over this notation now. It goes over, looks like vector AB in almost like two absolute value signs, okay? It talks about that's the magnitude of a vector. So magnitude is it represents the length of this line segment, like, especially if you're talking about like a plane, this might be like 30 miles or something, okay? So the magnitude of vector AB here would be 30 miles, okay? If that were the case. Alright. Next, your book talks about two vectors are equal if they have the same magnitude and direction, okay? So let's see what they're talking about there. How you like the fancy eraser here, paper towel. Alright, so they're talking about two vectors are equal if they have the same magnitude and the same direction. Let's see what that looks like. Got all this erased. Let's suppose that I have equal vectors here, okay? Say this is a vector, say that's a vector, okay? Maybe I'll position them like this. These are equal because why? They're facing the same direction, right? They're pointing at the same direction, okay? And they have exactly the same length, okay? The nice thing about these vectors is they're equal as long as they have the same length and they point in the same direction. So in other words, if I have a vector that looks like this and a vector that looks like that, I can rearrange these. I could scoot this vector here, I could scoot the vector there, I could scoot this vector here, I could scoot that vector there, however I need it, because no matter how I scoot this vector, as long as I don't change that direction or this length right here, it's an equal vector. So how does that help us? How does that help us? Well, a lot of time what we like to do is we like to put these on a coordinate plane. And if I have a vector sticking out over here, it's much easier if I translate it right here and put it starting at the origin, okay? That makes the math a lot easier to do on it. And I could do that as long as I'm not changing the direction here and the length. I could go ahead and translate it to that origin as I would like. Alright, let's see what else we have. If we look at page 2 of our notes, we have find the magnitude of the vector. And it says the vector is called vector U, and has the initial point R and terminal point S. Alright, so in this example right here, they say I have a vector where I have initial point R, 9, negative 3, and I have terminal point 6, comma, negative 1. Alright, let's think about what this vector looks like. If I were to draw it on a coordinate plane, okay? It has an initial point, 9, negative 3. So let's plot 9, negative 3, just somewhat. I don't care about getting exactly where it's supposed to be and so forth, okay? So I'm going to call that 9, negative 3. Then it says it has a terminal point of 6, negative 1. So let's go to 6, negative 1, maybe right here, okay? 6, comma, negative 1. Now what happens? Initial point here, terminal point there, so my vector looks something like that. Now what do they want me to do? They want me to find the magnitude of it, right? And what do they say that vector is called? Vector u. So they say this is vector u right here. Let's find the magnitude of vector u. Now to find the magnitude of vector u, here's vector u, here's the symbols for magnitude of vector u. How do I find the vector u? Well, what am I finding? I'm finding what? The length of this vector, or the distance from this point to that point. Now, what did I just say? The word distance. Huh. Maybe I'll use the distance formula then. Remember the distance formula is x2 minus x1 squared plus y2 minus y1 squared. Ooh, you had to blow some dust off of that one, I bet. It's been a while since you used it. Alright, so let's see. So that'll be what? The square root of x2. I guess we could use what? 6 maybe? Depends on how I label these actually, okay? Let's go ahead and call, I'll tell you what, let's go ahead and call this x1. We'll call that y1. Let's go ahead and call that x2. Let's go ahead and call that y2, okay? I want to stay standard what I wrote in my notes. Alright, so x2 minus x1 is what? 9 minus 6. And I must square it. Plus y2 minus y1, which is negative 3 minus negative 1. Negative 3, I'm going to put plus 1 squared. Alright, let's just calculate. What does that give me? Square root of 3 squared, which is 9, right? Plus, what is that? Negative 2 squared or 4? So what does that give me? The square root of what? 13. Square root of 13. Do not take the square root of each one of these if they have a sum. Alright, that was easy enough. Just had to remember the old distance formula we haven't used in quite a while. Alright, then it talks about representing, next in your notes is representing vectors visually. Alright, so what if I want to take two vectors and I want to add them, okay? Let's say that I have a vector that looks like this, okay? I'm going to call that vector u. And let's say I have a vector over here, vector v, that looks like that, okay? And I want to add these two. Now, I'm going to do adding them visually here, okay? What we normally draw in our picture and so forth. Because what we're going to have is later on we're going to have, like, say, an airplane's heading this way and the wind's blowing against it, and it's going to make the airplane actually go more that way. So we're going to look at drawing vectors and adding them and so forth. Alright, to add these, a couple of different methods you could use. You could use tail to tip method, okay? Tail to tip method says this. It says take one of your vectors, put the tail of it, or the initial point of it, at the terminal point of the other. Or put the tail of this vector at the tip of that one, okay? So in other words, I would draw vector u again, just like it is right here. Then I would take vector v, and I would take it and then put it over right here, okay? Now remember, I could put it right here, vector v, as long as I Do not mess with the direction of it or the length of it, right? So now what that forms, whenever I add these, is I want to say, okay, let's add vector u plus vector v here. Well, I want to start at the initial point of u, go through u, go through v, okay? And what that ends up doing is it ends up taking me to right here, okay? A lot of time we call it a resultant vector. I think this book maybe calls it the terminal vector. But anyway, this is vector u plus vector v using a tail to tip method, okay? Another method is the parallelogram method. Parallelogram method. Here's what this method looks like, the visual part of it anyway, okay? Take vector u, draw that. Here is vector u, okay? Take vector v, and what you're going to do is you're going to arrange it for this method, the tail of this one on the tail of that one, okay? So take the tail and put it up against the other tail, like this. And that's vector v. Now if I want to add u plus v, here's what I do. I make a copy of vector v right here, and I put it up here. I put the tail of vector v at the tip of vector u, and I make it look like that. Then I make a copy of this vector and put the tail of it at the tip of vector v, and it looks like that. Now my resultant vector is going to be from where the tails match to where these tips over here match. So my resultant vector is going to look like that right there. That's vector u plus vector v, okay? As you can see, we're at the same spot basically, okay? And if I would have used graph paper, you would see I was actually at the same spot. Alright, so that's a visual representation. That's going to help us later on whenever we look at word problems. Alright, then it talks about taking a vector and multiplying it by a scalar. Alright, let's suppose I took 2 times vector u here, okay? What would happen? I would scale it by a factor of 2, so I'd make it twice as long. So 2 times vector u would look something like this right here, okay? It'd be twice as long. 1, 2. And what happens whenever I multiply vector u by a negative value? Like let's say I take u and multiply it by negative 2, okay? What's negative 2 times vector u look like? Well, it's going to make it now have a magnitude or length twice of what it was, but the negative is going to turn around the direction of it, okay? So negative 2 times vector u is going to look something like this. It's going to have the same magnitude as this one, but the direction is going to be turned in the opposite. Alright. Next we have component form of a vector. Component form of a vector. Let's see, if you hear me say component kind of funny, it's because I had a teacher that taught me this with a very strong Boston accent. And I would tend to say component like here. Component form of a vector. Alright, your book says, let P be the point that has x1, y1, and Q be the point that has x2, y2 in the coordinate plane, okay? Instead of reading all that to y'all, I know y'all can read at this point. I made it to college. Alright, they're saying, suppose we have an x and a y axis here, and I have some vector here with an initial point of P, which is given by the order pair x1, y1, and a terminal point up here, Q, which is given by x subscript 2, y subscript 2, okay? So we have a vector like that, it says. Then it says, let V equal to vector PQ. So we're going to say this is vector V right here, okay? And then it does something like this in your book. It draws, it makes basically a right triangle right here, okay? Then it says vector V vector b, we can write it in component form by doing this, by taking the x values and subtracting them. So how do they put it here? x2 minus x1, comma, y2 minus y1. And then instead of writing it as an ordered pair here, what they do is they write it in this notation right here for a vector. That usually denotes a vector. So what are they saying? They're saying this part they call the components. And the way you find those is you subtract the x values and you subtract the y values, okay? In other words, when you subtract the x values, you just find the length right here. The y values, you find the length right there. Alright, so let's see. Let's look at the next part. A vector with its initial point at the origin is said to be in standard position. A vector with its initial point at the origin is said to be in standard position. So they're saying, let's say I take the same vector and I don't mess with the direction any, I don't mess with the length of it any, but I take its initial point and put it right here, and I'm going the same direction, the same length, okay? Then this is what we call standard position. Notice this initial point is at the origin here. All right, now the components are going to look like this here. Here's my fancy eraser. There it is. Okay, suppose we call that vector b. We say the components are given by a, comma, b, where this is the point. A, comma, b, okay? Write that a little better. The vector notation. Alright, so that's said to be in standard position. Let's look at this example on page 4. Given a vector v with initial point p and terminal point q. Alright, so they're saying we have an initial point p, negative 1, 4, and a terminal point q, which is given by negative 3, comma 8. Part A says, write the component form of vector v. Write the component form of vector v. So vector v, I'm going to say, is the numbers in this kind of notation, okay? Now, what are those numbers? How do I find the component form? Well, I take the what? The x value in my terminal point and subtract the x value in my initial point, comma, the y value in my terminal point, and subtract the y value in my initial point, and just do the math here. Alright, so that's negative 3 plus 1, or negative 2, and what is this, 4? So here's the component form of vector v. Alright, part B says what? Sketch vector v from P to Q. Alright, so I'm going to do a rough sketch here. I'm going to say, here's my x-axis, here's my y-axis. From P to Q. P is what? Negative 1, 4. So negative 1, 4 is maybe about right here. I'm going to put negative 1, comma 4. And then what? Negative 3, 8. So negative 3, 8 is going to be somewhere over here. Negative 3, comma 8. And that's my terminal point. So I'm going to have an arrow on that point. And my initial point's here. So I'm going to do something like that. Alright, part C. Sketch V in standard position. Part C. Sketch V in standard position. Alright, here's my x-axis. Here's my y-axis. And standard position means I want to move that initial point to the origin, right? So whenever I move this, I want to make sure I move it and don't tilt it and don't change the length any, right? So the way I do that is I look at this component form, negative 2, 4. Go to negative 2, 4. Plot that. Negative 2, comma 4. And start at your, that's going to be your terminal point. Start at your origin as your initial point, and it's going to look something like that. And mine's not exactly pointing the same direction. And the whole reason why is because I'm not using grid paper here, and I'm not drawing this thing really. I'm not making the X ticks and the Y ticks the same length. Let me see. Let me try to do that here. Let's see. So 4 is about right here from what I did before. And negative 2 would be about that long. So maybe it would look more like this. Still my magnitude's not the same, but You kind of get the picture. Here is negative 2 comma 4. And let me draw that like that. Okay, so if you draw this in grid paper, we'll be pointing the same direction and we'll have the same length, okay? The standard position means what? Put that initial point at the origin.